Dear students, after studying this module, you shall be able to know about the helicity and the chirality due to the helical shape of some molecules. Understand the Cram's and Prelog's rule. Learn about the correlation of the configuration of the newly created chiral center in the preponderant diastereomer with that of the existing one. Analyze various cases of helicity. Dear students, in this paper, we have different and varying concepts relating to the stereochemistry like conformational analysis, stereospecific and stereoselective synthesis, and chirality of many interesting molecular species. Now, we are at a stage where we are aptly equipped in our knowledge base to start topics of higher understanding like chirality due to the helical shape and Cram's and Prelog's rule. These topics provide deeper insights into the understanding of the stereochemical aspects of the molecules. Helicity presents a special case of chirality axis in molecules with the helical shape. Correlation of the configuration of the newly created chiral center in the preponderant diastereomer with that of the existing one takes into account some rules known as Cram's and Prelog's rule be discussed at length in this module. Helicity. A special case of chirality axis appears in the molecules with the helical shape. A helix is inherently chiral and is non-superimposable on the mirror image. Helices are chiral objects that look like screws and can therefore be right or left handed respectively. In nature, this type of chirality is frequently found, for example, in mussel or snail shells. A helically shaped molecule that is of a great interest for chemists and biologists is deoxyribonucleic acid, commonly called as DNA, which appears in two right-handed A and B helix and one left-handed Z helix types of helices. The DNA backbone is winded around the chirality axis. A helix rotational sense or helicity can be ascertained by following the chirality axis from the end of the helix. It does not matter from which end of the helix the molecule is viewed, because the result of ascertaining the helicity of a particular molecule is always the same. Optical rotatory dispersion and circular dichroism provides interesting experimental study of polypeptide helicity. A helix may in fact be considered as a manifesting axial chirality, its axis serving as the chiral axis, although it is more convenient to discuss chirality of this type under the heading of helicity. If it has a C2 axis perpendicular to the axis of the cylinder, the helix is called palindromic. For assigning the chiral designation to the helix, if moving from one end to the other along the axis, the helix describes a clockwise direction, it is designated P plus, and if it describes an anti-clockwise direction, it is designated as M minus. The different helical structures with the P and M designations are shown here in the figure 1. Helicity in a molecule may also result from the molecular overcrowding. This manifested in molecules such as helicenes, benzphenanthrenes or even phenanthrenes as shown in figure 2. These molecules are normally expected to be planar, but due to molecular overcrowding, the ring structures assume a helical shape. The terminal rings and the substituents are in different planes and the molecules exist as two helical enantiomers. Hexahelicene structure A as shown in figure 2 is a classic example of a stable helical molecule with exceptionally high optical rotation, alpha d being 6200 degrees. Higher helicenes, example hepta and octa etc., are also known. The chiral designations of the molecules A, B and C are P, M and P respectively. The first two have a C2 axis passing through the central ring junction of the molecule with the two planes of the terminal rings symmetrically oriented around it and belong to the C2 point group. It is often very convenient to specify the chiral descriptor of the conformational or 8-trop isomeric enantiomers from such a substituted ethanes and biphenyl derivatives with the axial chirality by helical nomenclature P and M. Some of the rules are listed below. The substituents are ordered in 3 in the case of ethanes and 2 in case of biphenyls as shown in figure 3. The highest priority group as per the CIP is selected in the front fiducial group and related to the highest priority group at the rear. If in doing so a clockwise turn is described, the configuration is P and an anticlockwise turn on the other hand is M. This is clearly illustrated in the two enantiomeric conformers of mesotartaric acid as shown here in figure 3. For studying the specific case of biphenyls, we can consider the case of S-dinitrodiphenyic acid. The two fiducial groups are nitro in the front and NO2 in the rear. Movement from the former to the latter takes place in the clockwise direction and so is represented as P helix. The enantiomer of this form is an M helix. In biphenyls, R corresponds to M and S to P. Shown here the two enantiomeric forms P and M of the acyclic conformers. Cramp's rule and Prelog's rule. Correlation based on the asymmetric synthesis. When a new chiral center is formed in a molecule which already contains one or more, two diastereomers are formed in unequal amounts. The reaction is known as asymmetric synthesis and the existing chiral center or centers bring about asymmetric induction. A few empirical rules have been proposed depending on the substrates which correlate the configuration of the newly created chiral center in preponderant diastereomer with that of the existing one. Cramp's rule. When ketonic group attached to the chiral center, for example, R C double bond O C R1, RL, Rm and Rs, where L, M and S stands for a large, medium and a small group respectively, undergoes a nucleophilic addition with the organometallic or a metal hydride reagents, two diastereometric products are formed, erythro and thrio, one of which is always going to predominate. The relative configuration of the predominant isomer can be predicted by Cramp's rule based on some arbitrary models. Cram and El-Hafez 1952 gave these rules. In the open chain model as shown in the structure 1 in figure 4, the ketonic group is flanked by two smaller groups Rs and Rm, with the large group Rl nearly eclipsed with the R, which is shown in figure 4. The metallic part of the reagent gets complexed with the carbonyl group and the carbonyl equivalent of the alkyl group R dash or H is transferred to the trigonal carbon from the sides of the R with the which are smaller in nature in preference to that of the medium sized R groups. That is, route A is preferred over the route B to give the structure 2 as shown in the figure. Although no mechanistic rationalization has been claimed, it is reasoned that carbonyl, being a complexed with the reagent, becomes effectively the bulkiest group and is thus better placed between the RS and RM. Two examples are given in figure 5 which illustrate the rule and are self-explanatory. It may be noted that although only one enantiomer of the substrate is shown, the rule is equally applicable to the racemic substrate, and in which case the products are also racemic. Although the model correctly predicts the stereochemical course of reactions, it often fails to give quantitative assessment of the asymmetric induction in terms of steric interactions. From mechanistic considerations, a few alternative models have been suggested, of which Felkin and model in the year 1980 has gained consensus. In this model, two reactive conformations as shown in structure 3 and 4 in the figure 6 have been considered, in which either the largest RL or the most electron withdrawing group, which provides the greatest sigma star pi star overlap with the carbonyl pi star orbital at C alpha, is placed at right angle to the carbonyl double bond. Between the two, the first with R medium sized Rm opposing carbonyl group and Rs gauche to R is usually preferred. The non-bonded interactions which involve R dash and Rs rather than R dash and Rm as in structure 4 are thus minimized. The model predicts the same stereochemistry as CRAMS, but provides a more quantitative assessment of 1-2 asymmetric induction. A third conformation, as in structure 5, may make some contribution but in generally ignored the unfavorable steric interactions. If the chiral center in the ketone contains an alpha group such as OH, NH2 and OMe, which is capable of coordinating with the reagents, the stereochemistry of the product is predicted by Cram's rule based on rigid chelate cyclic model as in structure 6, all shown in figure 7, in which the metallic part of the reagent is doubly coordinated to form a 5-membered ring. The nucleophile preferentially approaches the electrophilic carbon from the side of Rs, as the example follows. If the chelating group is Rm, which is often the case, the cyclic model predicts the same stereochemistry as the open chain model. But if it is Rs or Rl, opposite stereochemistry follows. Asymmetric induction through chelate model is usually high. If a strongly electronegative group, example, a halogen atom is present at C alpha, yet another model, a dipolar one, is suggested for prediction of the stereochemistry. The dipoles of the carbonyl bond and the CX bond oppose each other, and so they are placed anti as in the given model, as shown in figure 8 and structure 7. The dipole repulsion is thus minimized. The electrophilic character of the carbonyl carbon increases and the nucleophile adds from the side of Rs, giving the major product as shown in the figure. The Felkin and model, as in the structure 8, in which the electron withdrawing X group is placed perpendicular to the carbonyl bond, also predicts the same stereochemistry. Prelog's rule. Prelog's rule, which correlates the configurations of the chiral alcohols with those of the alpha hydroxy acids, especially mandelic acid and etrolactic acid, is the outcome of generalization of the results of asymmetric synthesis carried out by McKenzie group in the early part of the century. When phenyl glyoxylic acid is esterified with optically active alcohol, for example, menthol, and the ester is reduced with sodium amalgam or with sodium borohydride, mandelic acid enriched in one of its enantiomers, in this case R minus, is obtained after complete hydrolysis of the product. The reduction step has now been replaced by Grignard addition of methyl magnesium halide so that the configurationally stable heterolactic acid is produced. Prelog's rule correlates the configuration of the hydroxy acid, that is heterolactic acid with that of the alcohol as follows. The ester of phenyl glyoxylic acid is so written that the two carbonyl groups are anti-periplanar as in the structure 9, figure 9, and the larger group RL at the carrying at C4 at the chiral center of the alcohol moiety is on the same side of the ketonic carbonyl. RS with hydrogen and Rm at C2 are in back and front of the plane respectively. Methyl magnesium bromide approaches the electrophilic carbon of the ketonic carbonyl from the side of Rs more easily than from the side of Rm. The preferred diastereomer is thus 15, which on complete hydrolysis affords heterolactic acid enriched in R minus enantiomer. The carbonyl carbon in the menthol has R configuration and it follows the obtention of R minus heterolactic acid from the above sequence of reactions. Esterification of an alcohol with phenyl glyoxylic acid, Grignard addition of methyl magnesium halide and subsequent complete hydrolysis of the product settles the configuration of the chiral alcohol as R. Similarly, if S plus heterolactic acid is obtained, the configuration of the alcohol is S. This is illustrated with the two steroidal alcohols 7 alpha and 7 beta hydroxy cholestane figure 10. The asymmetric induction is usually moderate 10 to 30%, but is sufficient for the correlation of the configuration. Since the configuration of heterolactic acid is known, the method gives the absolute configuration of the chiral alcohols. As in the Cram's rule, this is formal and not a mechanistic assumption. Alternative conformation with Rs in place of Rl may also be considered, in which case it is a choice between the approaches from Rm side versus that from the Rl side. The former is preferred and the same stereochemistry results. To summarize, a special case of chirality axis appears in the molecules with a helical shape. A helix is inherently chiral and is non-superimposable on its mirror image. Helices are chiral objects that look like screws and can therefore be right or left-handed respectively. Helicity in a molecule may also result from molecular overcrowding. This is manifested in molecules such as helicenes, benzphenanthrenes and even phenanthrenes. When a new chiral center is formed in a molecule which already contains one or more, two diastereomers are formed in unequal amounts. The reaction is known as asymmetric synthesis and the existing chiral center or centers bring about asymmetric induction. Cram's rule and Prelog's rule can be used to predict the relative configuration of the predominant isomer.